This is about something completely different than you are used to. I want to take you for some simple cup and rubber games to some very strange set theory. Well, graph theory on infinite graphs. So I assume everybody knows what graphs are, so we're not going to define that. These cup and rubber games actually started in the late 70s when some spelunkers asked Tori Parsons to help them find somebody lost in the caves. That developed into what's called sweeping of graphs, where you know that on a graph you have somebody somewhere on an edge, on a vertex you don't know, and you want to make sure that you find that person. So you have to sweep all the edges somehow and make sure that the person that's lost or trying to evade you cannot come back through the part that you've already searched, and so on. So there were some papers on that, and then that subject died until about 10 years ago when Danny Dyer wrote a PhD thesis on it, and so they revived that subject. But that's not what I'm going to talk about. There is another subject that appeared around the same time, possibly as a result of the work of Tori Parsons, and that's the game defined like this. You take a graph. Here's a graph. And the game is played by two players, a cup and a rubber. And this is the basic game. There are many variants I'll mention in a minute. The cup chooses a vertex. A rubber chooses a vertex. That's round 0. And then each subsequent rounds, cup can move the vertex adjacent to it, and then the rubber moves the vertex adjacent to it. And we assume that we are on reflexive graphs so that they can stay put. Okay? And of course, the object of the cup is to occupy the same vertex as the rubber. And the object of the rubber is to evade the cup. A graph will be called cup win if the cup has a strategy to catch the rubber. Now, I will not define the word strategy, but it is not as obvious as you think. Okay, there are some subtleties in there. In fact, there is a paper coming out about the subtleties of this, which relates subtleties of that game to some problem that Zermelo and Koenig corresponded about 100 years ago. Okay, so we have the game. So what are the questions that we can ask? Well, there are two obvious questions at least. One, when can the cup win? That is, I give you a graph and you tell me, can the cup win? And question 2 that's related is, how many cups are needed? I shorten what I'm right. I say much more. It's obvious that if you put a cup on every vertex, then you're done. So there is an upper bound, this is finite, so there is a minimum number of cups that you need to catch the rubber. Examples. This is obviously cup win. You put the cup, you can be wasteful at one end and just go. This I don't put the loops in. Just imagine that. This obviously is not cup-win, but 2 cups are enough. Okay? So that's for those questions. Now, before I go on with this, there are many variants that appeared later, in the later 80s and 90s, Seymour, Beanstalk Company, that you can change the rules of the game. You can put the cups in a helicopter and they can be dropped off somewhere and picked up again and so on. And there are many other variants. And some of these variants give you a very nice relationship between the number of cups needed and a graph width. The helicopter, you get tree width. Then you can also have a path width and so on. For this graph, for this game, the relationship with two widths is not very simple. There's a paper by Kaminsky and company, Jaurès, where they show that the number of cups is bounded above about twice the tree width. But if I remember correctly, but there's nothing more precise than that is known for this game, for this particular game. But this is the game I'm interested in. Okay. In fact, the number of cups to find out how many cups you need for a graph is an XP-compete problem. That was proved. It hasn't been published yet. It was proved recently, and it's under review. But so let's look at this first problem. How could you go about showing that a graph is cup-win? Well, what you do is two things. This is from a paper by Novakovsky and Winkler in the early 80s, and also independently done, the finite part anyway, by Alain Keogh in his thesis and some papers. By the way, if you want a big survey of all these things, there's a big paper of about 5 years ago by Fomin and Tilikos, which is an annotated bibliography. It's on their webpage. So these people, for the finite case, did something that's, in retrospect, is obvious. They looked at what happens at the end of the game. So at the end of the game, you have a cup somewhere. You have a rubber somewhere. So this is Robber's last move. After he moves, he will be caught, no matter what he does, because we are in a cup-win graph. Mm-hmm. Okay? So what does that mean? That means that there must be an edge here, because if Robber decides to stay put, he must be caught. And wherever he can go, well, the cup can go there as well. Right? And of course, if Robber decides to go there, then the cup stays there. So what it tells you that the closed neighborhood of Robber's vertex is contained in the closed neighborhood of the cup's vertex. So that's observation number one. Observation number two is that if you have this situation, and you can get a retraction from the original graph to a new graph, which is small. You just retract this vertex to here. Right? Every edge down here becomes an edge here. This thing becomes the loop that's there. So it's a retraction. Everybody knows what retraction is.
Contraction.
Retraction, as in homomorphism. Oh, okay. Define that.
Different from contraction?
Yes. Yes. Okay, everybody knows what a homomorphism is? Okay, a retraction. I'll give you one of the many equivalent definitions. Rho, say, is a mapping from the vertex set of the graph to itself, probably smaller. Okay, because of H, where H is a subgraph of G. Okay, such that rho is a homomorphism. That is a mapping from the vertices to vertices that preserves edges. An edge must go on an edge. And rho restricted to G is the identity on H. Okay? So this is a retractions because I just fold this vertex here and everything else stays put. Okay. And then you have to prove a lemma, which I will not prove because it's a very nice exercise. You can prove it yourselves. Very simple exercise. If H is a subgraph of G, rho from, I'll write it G to H, is a retraction. And if G is Kopwin, then H is Kopwin. And what you do is you play on H as if you were on the image upstairs. Okay? And in fact, for a retraction like this, it's an if and only if. But with this and this observation, we have a theorem. A graph G is Kopwin if and only if vertices of H can be ordered V1, V2 to Vn, so that for every I in 1 up to n, which I will denote n, there is a j in n bigger than I, such that the closed ith neighborhood of Vi is contained in closed ith neighborhood of Vj, where ni of a vertex is simply the neighborhoods of the vertex in Vi plus 1 Vn. So think about it graphically. If you order the vertices, pick a vertex I, pick a vertex, there must be a vertex J, so that closed neighborhood of this and this, so everything that's adjacent up here, this one is also adjacent to. So in particular this one, because it's a closed neighborhood. Okay? Then just follow from these two things. Okay. Let's erase. So, what does that tell us? That tells us that some classes of graphs are Kopwin. Does this look familiar to anybody? This kind of ordering? to you certainly. Now, corollary. Chordal graphs are coupling. Right? Chordal graphs have simplicial vertices. This is this kind of ordering. Corollary 2. Bridge graphs are coupling. What's a bridge graph? Anybody know? Okay. What's a chordal graph? Chordal graph, if you take a cycle of length at least 4, must have a shortcut, chord, right? Bridge graph, every cycle of length at least 4 must have a shortcut. That is, the distance in the graph is shorter than either of these parts. So a graph is bridged if whenever you take a cycle of length at least 4, there are 2 vertices on it whose distance in the graph is smaller than the distance on the cycle. Okay, so it generalizes chordal graph. There's a theorem by Martin Faber and Robert Jamieson. I mean, there's a bunch of papers by Faber and Jamieson about bridge graphs. And one of the key results, one of the basic results, is that a bridge graph contains an isometric vertex. An isometric vertex is one that if you remove it, the distances between the remaining vertices don't change. Again, an isometric vertex is a vertex so that in the remaining graph, the distances don't change if you remove it. Okay? And if you remove an isometric vertex from a bridge graph, it remains bridged. So you get an ordering like this, and the graphs are coupling. Again, it requires a little bit of work. In fact, there is a theorem by Anstey and Faber which says a graph is bridged, this is sort of on the side, if and only if it is coupling and has no sorry, I have a blank. There's no induced, I think I reversed it, cycle. No, so it's okay. Cycle of length 4 or 5. No, I have it right. Because you cannot have this, that would not be bridged, and similar with the 5 cycle, okay? So that's just on the side. Okay, so we have bridge graphs which are coupling. So now we forward to Japan, 1986. Sitting over dinner at the banquet in the Hakone conference, these two people asked me, are infinite bridge graphs coupling? That's an interesting idea. I have some open problems about bridge graphs if you're interested. But so are infinite bridged graphs coupling. Let's just stay countable. Well, that is sort of obvious, no? If you know any pedagogy, you say by compactness, it doesn't work. Compactness doesn't work here. It doesn't apply. It's not first order. So you want to recover compactness, maybe. Well, then you work a bit, and you come up with a bunch of conjectures, and one of them is that you can bound the number of rounds a cop needs to win in a coupling graph. And you would like to bound it by some known parameter, like diameter or whatever. Sorry, it doesn't work. There are some very simple examples where all the obvious graph parameters are unrelated to the length of the game. In fact, nobody knows how to compute the length of the game by a formula. We have an algorithm that can calculate it, which is polynomial if you fix the number of cops. It's not if you don't. But there's no formula. So it's one of open problems. Is can you compute? Can you do better? Can you do some better calculation of how long it takes to catch a number? So you play with it for a year or two, and you come up with the following theorem. This is me and François Laviolette, Norbert Sauer, and Robert Woodrow. And the theorem says this: for any k there is a chordal graph that's better than bridged chordal of diameter 2, that's pretty strong, diameter 2, on which the cop needs k rounds. Now this is something compactness can be applied to. And so you get a corollary. There is a graph, a countably infinite graph. Which is chordal, diameter 2, and not coupling. I can actually, the whole thing started off with François Laviolette's construction of an example of such a graph, which we can then generalize. And I can actually say for any Aleph alpha, I can give you a chordal graph of diameter 2 of cardinality Aleph alpha, which is not coupling. Okay, it's sort of grow with sort of a binary tree like this out there, and then you have to make sure it's connected to, and each vertex is sort of an uncountable set where you do things. It's a bit of a mess. It takes about 2 pages of description in the paper, if you want. So it's not very pleasant to read. So that's the first example of why infinite graphs behave completely differently from finite graphs in this respect. Okay. You can ask, okay, how many cops do I need? Well, it is more complicated, but you can make the following observation. Okay, call it a theorem. Sorry. Does everybody or anybody know what the Rado graph is? Or the random graph? Or the ultra-homogeneous countable graph is? Anybody? No? Okay, let me spend 5 minutes talking about this, okay? So this is a graph which is defined on the natural numbers, say, and is defined in several different ways. The first, the most common definition today is you take a coin that's unbiased, if it exists, an ideal coin, and for every pair of vertices, you flip the coin. If it's heads, you put the edge in. If it's not, you don't. That gives you a graph. There's a simple exercise, simple argument, which shows that in this graph, whenever you take two finite sets of vertices, A and B, there is a vertex which is adjacent to all of A and nothing in B. Just calculate the probability this happens, take the limit. Okay. This is one of the defining properties of what is called an ultra-homogeneous graph. Ultra-homogeneous graph is a countable graph, again on this set of vertices, which has a property that if you take two copies of the same graph in there and an isomorphism between them, say phi, then there is an automorphism of this graph, let's call it R for Rado, such that phi restricted to H is, psi restricted to H is phi. So any isomorphism between pieces, you can lift up the automorphism. It has this property, and with this property, you can actually construct such a piece from scratch. You take a vertex, add something, one vertex set, empty set, you add something which is adjacent to one or to the other. Then you flip the roles, so you have to start with vertex, so you have to have something adjacent to it, something not adjacent to it. And then repeat. For every subset of this, you use this property to repeat, and you construct a graph. You can use this property to prove that if you take two graphs like this, say R and R prime, then these are isomorphic. Again, you just take one vertex here, one vertex here, have an isomorphism going from there. Use this property to say, okay, this is here, I take something there. Then you start on this one, you take something here, you construct it there, and you just go back and forth. The technical term is a back and forth argument, and you construct an isomorphism with these two beasts. Okay, this key property shows that this graph is not COP-Win. Because if, see, the COPs are here, and the rubber is here, then there is a vertex which is adjacent to the rubber, but to none of the COPs, so you can go there and repeat. So the COP can win. Sorry, the COP cannot win, the rubber wins. Okay, so write this observation. R is not COP-Win. In fact, corollary, same argument shows no finite number of COPs can win on R. Same argument. Okay. So one other question you can ask is, how dense do you need the cups in the graph to win? What's the proportion of the number of vertices that the cups have to be in? Here you have Aleph0 vertices, and this shows that you need Aleph0 cups. Well, how many cups, how dense do they have to be? Do they have to appear, say, if you look at the integers, do they have to be every third one, every fifth, every hundredth? If you define the ratio of the number of cups to the number of vertices, call it Rn, if you take an n vertex subgraph of what you have, well, you would like to actually construct sort of a tower of graphs, finite subgraphs, okay, with n1, n2, n3, n4, and so on, so that if you take the union of all these, you get the whole graph. Then you could calculate this ratio for each of these subgraphs and take the limit if it exists. And then it turns out that any R you choose can be constructed this way. We can give me an R, I will give you a tower of graphs whose union gives you the thing, and where the limit of the number of cups that you need is that. So you can go from almost no cups, density 0, 0, 0, 0, 0, 0, 0, 1, to almost everybody has a cup in it, to 0.999999999. Anything is possible. It's very weird. Again.
So you mean the optimum ratio of cups?
It's not known. It's not well defined. Because depending which tower you choose, you can get different ratio. Okay. So it's not, you cannot define the optimum ratio.
Right.
Yeah, right. It's also a very strange thing. Okay. So here's one other weird thing. Here's an exercise which is amusing. I call it a theorem, but in the paper of Nowakowski and Winkler, it's a remark on the side. I'll just, for our benefit, I call it a theorem. A finite, regular graph is not cup-win unless it is complete. And again, this is a really easy exercise on counting. Just count the neighbors, essentially, and you will see that the rubber can always escape. So next thing I want to indicate how to prove, I will not go through the whole proof, is that I'll give you the whole schmucks. For every ordinal alpha, there is there are 2 to the alpha non-isomorphic cup-win vertex transitive graphs. But let me show you one other thing that I forgot to mention. before I get to that, which is simple and easier to understand. So when I talked about this result at SFU, Boyan Mohar said, but for me,
consider the cardinality of the graphs. Do the graphs have some?
oh, sorry, did I say, yeah, thank you. I said graphs of order, thank you. Aleph alpha. Thank you, of course. So Boyan Mohar says, for me, infinite means countable. So, observation. That's actually not due to me, but to Mark Gavenchak. Countable graphs are Roberwin. That is, are not Kopwin. The reason is Koenig's lemma. Koenig's lemma says that if you take a tree, which is infinite, and in which every degree is finite, then there is a ray in it, an infinite path, starting from any vertex. Again, that's an exercise, a very easy exercise to prove that. And to prove this is like that, you need to be a little bit careful. You pick any vertex where you put the cup. Now, where will the rubber go? Well, what the rubber will do is construct a breadth search tree. So these are all the vertices of this. It's finite, right? All the neighbors of this, and so on. And it will, in that tree, will go a distance at least 2.
So in the definition of countable graphs, do you make sure that locally it's finite?
No, I just countable, locally finite. Sorry, forgot. Thank you very much. Must be locally finite, otherwise.
What does it mean, locally finite?
Locally finite means every degree is finite. Only finite number of neighbors. So you can do this. And then the rubber will go a distance at least 2, and then that's it. Not anywhere. From this vertex, there must be a ray somewhere by Koenig's lemma. So he will go a distance at least 2 on that ray. And then Kopp can go closer, but he cannot jump because this is the breadth first search tree. Is that clear? Okay. So, let me show you something much more complicated. This. What I will explain, briefly at least, is how to construct a vertex transitive graph out of any graph. And then you can observe, again, I can send you paper, but you can prove that the new graph is Kopwin if and only if the graph you started with was Kopwin. Okay? To prove the theorem that I just erased over there is a bit more complicated, because to get 2 to the Aleph alpha of them, you need to get lots of non-isomorphic graphs to start with, and we're not concerned with this at the moment for this part. But I can show you how to construct it from any graph, a vertex transitive infinite graph. Okay? And
What is vertex transitive?
Okay. G is vertex transitive if for any u of v in G there is an automorphism, say phi in the automorphism group of G, such that phi of u is equal to v. So all the vertices look the same. In particular, the graph is regular. Okay? So what you want to do is this. Fix a graph G. I need this now. And fix, say, a kappa greater than or equal to size of V. And you want it infinite. Construct an index set V cross kappa. Construct a vertex set V. Oh no, this is define F. That'll be all functions from the index set to the vertex set. Construct a graph G, say tilde, or G sub kappa, say, to have vertices, these functions, and you connect two functions. F G will be an edge of this. If f of I is equal to g of I, or sorry, I should say for each I in I, either f of I is g of I, or f of I and g of I are adjacent. So if these be functions, this generalizes the Cartesian product, like this. Okay. The problem with this definition is that it can happen that you start with a connected graph, and this thing is not connected. The example that you can think about it is an infinite countable star, where we have a central vertex and you have paths of all lengths. And you cannot get from the middle vertex to the vertex which contains all these, because there is no finite way of getting there. You'd have to change infinite number of coordinates. That's an infinite distance, so that's not connected, okay? So we have to do something a bit better. And we can do this. We can fix a function b in f defined by, it's a projection, b of u alpha is equal to u. Let f sub b be equal to the set of functions from I into v, such that f of I is equal to b of I for all but finitely many I and I. And define kappa G to be the graph F sub B, E sub B, say, with E sub B, the set of functions G, such that either Fi is Gi or Fi and Gi adjacent. Same definition as here, except you have different, you take the functions from this set. Okay, now you can prove that if you start with a connected graph, this is connected. Theorem, kappa G is connected. Is a vertex transitive. I will not do a proof, but I can tell you, for those who are interested, what you have to do is show that any permutation of the index set gives you an automorphism. That's not very complicated. And then you have to observe, just observe that when you pull things back up from here to here, you can get partition of I for any vertex U and any vertex V, and you can get a bijection between I, and that's a permutation, so that's an automorphism. I don't have time to do that. It takes another 15 minutes, and but the point is that you now have a vertex transitive graph, and you can prove that if you start with a Kopwin graph, then this new graph will also be Kopwin. And so you have a bunch of interesting infinite graphs which are Kopwin and are vertex transitive, therefore regular. So it's another difference between infinite and finite. In the finite case, regular graphs are not Kopwin. In the infinite case, a bunch of examples. Okay? Okay. I have 2 more things to say. I hope I'll manage.
So is it trivial to prove that this is Kopwin, if G is Kopwin?
It takes about half a page in print. But it's not very complicated.
Is it true when for any G or for G which is vertex transitive?
No, for any G. That's a strange thing. For any G, kappa G is vertex transitive. Okay?
And E of B doesn't have any reference to B, right?
This B? Yeah, it has a reference to B. Because I fixed now a base function. I only take functions which differ from this one in a finite number of places.
Induced subgraph of GK or GK?
It's an induced subgraph of this.
Oh.
Yeah. But at least we can show that this is, if G is connected, then this is connected. That's an essential part of proving it's Kopwin. Because if you're a non-connected graph, then it cannot be Kopwin. Right? Because the Kop goes in one component and the robber will choose another component. It's finished.
Does it depend on the choice of bees?
Sorry?
Does it depend on the choice of bees?
We haven't investigated, but we defined a very particular B. It's a projection on you, right? So this construction actually dates back to the 80s to Wilfried Imrich. And what I want to say is these graphs are very weird. We'll go. So we proved all this, and then Robert Woodrow and I started thinking about what do these graphs look like? We don't know. I mean, it's very difficult. So if you think about it a little bit, if you start with a complete graph, then this resulting graph will also be complete. If you start with an empty graph, the graph will be empty. So we thought, well, let's look at the simplest graph which is not complete that we can think of and see what happens. What is the simplest graph which is not complete that we know of and which is not independent set, which is not independent? This one. I mean, you can't get much simpler than that. Turns out, if you do this with an infinite kappa, no matter whether it's countable or not, this to the kappa already has some very strange properties. It contains all countable graphs. That's weird. For any kappa, this contains all countable graphs. It does not contain an uncountable star, even if kappa is countable. Uncountable, sorry. But remember, the Rado graph contains all countable graphs as well. But it's not Kopwin. This one is obviously Kopwin. This is a Kopwin graph. If you believe the theorem which says that if you start with a Kopwin graph, then this is Kopwin. So this is a Kopwin graph. So you have a graph that contains all countable graphs, and they have also all finite graphs. But it's not the Rado graph, because this one is Kopwin and the Rado graph is not. So it's really very strange. And in fact, this part is work in progress. We still investigating properties. We still don't know more about it. They haven't looked at bigger graphs yet. It's just we are puzzled because it's weird. Okay. Okay. In the last 5 minutes, I would like to go back to the Nowakovsky-Winkler paper, because one question I could ask is, how can you tell that an infinite graph is or is not complete? It's difficult. So they also prove that if you take any graph, finite or infinite, it is Kopwin if and only if the relation that I'm about to define is trivial. That means everybody is related to everybody else. Okay? Well, it could also mean that nobody is related to anybody, but since some people are related to some others, then okay, define it as this way. Let phi 0 be the pairs. Oh, let me write it. Sorry, let me write it a bit differently. Relation R. Let light R0 be defined by U R0 U or U in V. Okay, that's the vertex set of the graph I will not specify. Okay. For an ordinal alpha, define R alpha by U R alpha V if there is for every x in the closed neighborhood of u, there is a y in the closed neighborhood of v, and a beta less than alpha, such that x is beta related to y. Now this looks like a lot of gibberish. What it really says that it takes 0 steps if the cup is on u and the rubber is on u. It takes 1 step if the cup is if the rubber is here and the cup is here. So the alpha really gives you a number of steps you need in the finite case. But of course this also works for limit ordinals, and so you can define it for an infinite graph. Now what happens is there is an alpha less than the cardinality, less than or equal to cardinality of the graph, such that R alpha plus 1 is equal to R alpha. Now I'm looking at them as sets of pairs. Okay? Clearly this you have everywhere here that R alpha is contained in R beta if beta is bigger than alpha. What was related before is still related. Okay? So let R be equal to R alpha. And there is at least such because these are ordinals, but we don't need that. And so that tells, okay, this is difficult to test for an infinite graph, but it gives you a polynomial time algorithm to decide in the finite case whether the graph is Gaussian or not. You just program this.
What does trivial mean?
Trivial means that every vertex is related to every other vertex. Everybody is related to everybody else. Okay? So this gives you, well, back to finite case, this gives you a polynomial time algorithm to decide. In fact, you can use this to write an algorithm that decides if you I give you k cups, okay, a graph, and you can, if k is fixed, you can decide in polynomial time in something like number of vertices to the k, I said maybe 6k or something, I can't remember, to decide whether the k cups can catch a rubber on the graph. So we're back from the infinite to the finite. And my time is up. I didn't give you the proofs of these things, but I don't have the time. If you want to see the proofs, come in about a month down to Mark Sigger's. I will give proofs. So, questions?
Okay. Thank you.